Hello everybody, I'm Nick, and this time I'm going to take a look at the Parallel class in C# and .NET and see if it's actually a class worth using. For those of you who don't know, the Parallel class has the for and for each method, which allows you to do parallel, for and for each basically, by segmenting it, then running it in multiple threads, and then aggregating the results back in a true multi-threaded fashion. Now, this is not to be confused with asynchronous programming and await async, but the reason why I'm mentioning that is because we are actually going to take a look at await async and how it might tie into that to maybe give us the best of both worlds in a specific solution. If you like that type of content and you want to see more, make sure you subscribe and this notification bell to get alerted when I upload a new video. So what do I have here? Well, first and foremost, I want to clear out a single misconception, and that is that just because you parallelize something, it is going to be faster. Many people think that, and it's not actually true. In this benchmark here, using benchmark.net, I have an array of 1,000,000 integers, and then I'm just iterating over a normal loop, for each loop, or actually for loop, and I'm setting the value for the index I am on. And then here I have the parallel class like I showed you, which has the for each and invoke method. I'm not going to take a look at the invoke one. I'm going to focus on for and for each, and then I'm iterating again in a parallel fashion, and I'm returning the array. So what I'm going to do is I'm going to actually run this benchmark, this very basic benchmark, to show you what I mean, that performance might not necessarily improve just because you used parallelization. So results are back, and let's take a look at that. As you can see, the normal for each, which is not using the parallel class, is 1 millisecond in mean time, and the parallel one is 1.3, so it is actually slower. And that's for multiple reasons, and it can be the quality of your CPU, how many threads you have, but it's also the fact that this number and this operation will be segmented to multiple effectively buckets and then aggregated back in, and there's an overhead in doing that, and sometimes, like in this case, it is actually not worth it. So don't just assume that because something is parallel, it is actually faster. Now, as a disclaimer for this whole video, I want to say that I do actually have a pretty good CPU with 32 logical cores and 16 physical ones. So any results in this video will vary based on your silicon. That's because parallel is true multi-threading, while something like await async doesn't necessarily depend on multi-threading. It will use at least 2 threads usually, but it won't go haywire like we're going here with a max degree of parallelism. So keep that in mind. Now, what I want to show you is this API parallel benchmark here, and this to me is a bit more interesting. So what I have is I have a bunch of API call tasks, 1,000 specifically here, that I put into an enumerable and then a list, and they will not fire just because they were created. They're wrapped around a function. So they are here, and I'm going to iterate over them and invoke them and await them. And I'm going to do that 1,000 times for the benchmark. And then here I have the parallel version of this, where I have a for loop with the count of the tasks, and then I'm awaiting those tasks here in the very same fashion. Now, the parallel class and the methods are not asynchronous, so you can't just do async here and await here. Technically, if this is an awaitable thing, it will compile, but it's actually an async void, which is an event if you do that. So it won't actually wait for the thing to actually run. Don't do that. Parallel.For or ForEach are not supporting asynchronous programming. So I have to do the getAwaiter, getResult to synchronize the operation. That being said, given the fact that it's parallel, we want to see how it will perform. And what this is doing is it's calling an API running locally on my PC right now. It's this one here, and it's getting back a number from that API. So just to recap, I am going over 1,000 items in a list, tasks, and I'm invoking them one after the other in this for each version, and then I'm getting the number back, which is a response from the API. And then I have a parallel version of this where I'm giving 1,000 things into the Parallel.For method, and I'm invoking them in parallel multi-threaded fashion. And I'm gonna go ahead and actually run this to show you how this will perform. And I'm also going to pull up the CPU utilization as this is running, because I think we're going to see some interesting things here as well. So let me just go ahead and click run here, and this will start. And this is now running, and you'll see that doing it in a serial way doesn't really stress my CPU necessarily. There was no spike, but after that, you can see that all the cores or logical processors here actually spiked to 90% because they made use of that parallelization. And as you can see, we have 107 milliseconds for the one after the other, and we have 10 milliseconds for the parallel version. So clearly there's a huge advantage here, 10 times faster if you use the parallel, even though it's synchronized. However, the fact that it's synchronized means that the CPU that's computing that is technically to a degree wasting clock cycles, because it can't do anything but await synchronously for this request to come back. So there's a drawback in doing that, but this also depends on your use case, so it's not necessarily a problem for everyone. Now, I don't think that just having this parallel version actually paints the full picture, and I'm gonna limit this a bit to something more realistic, because usually, at least working in microservices, you're probably gonna run within like a Kubernetes cluster or ECS or whatever Microsoft is using in Azure, and those environments can't really use those beefed up CPUs. You're probably going to have less threads or cores to work with. So what I'm going to do here is I'm going to copy that version here, and I'm going to add a value here called max degree of parallel. Why do I have to pronounce this? Parallelism? How parallel you want to be, basically. And then that's a value we can provide here in the for method. So I can say new parallel options, and I can say max degree of parallelism is the value provided. And then I'm going to break down this to two versions. One is the unlimited version. So parallel version with -1 means just detect how many cores I have and use whatever you want. And I'm going to do with 4 as well. And 4 is probably more realistic. So this is the unlimited parallel version, and this is the limited. And 4 or maybe 6 would be more realistic to what you would have in a production environment, I think, anyway. But this again depends on what you're doing. If you have a big monolith with a beefed up PC or server, then you shouldn't worry about this example. But I'm going to run it anyway just to get some numbers on what happens when you don't just let this use as many resources as possible. I'm going to run this and pull that back in. And the results are back, and as you can see, that's 115 like we said before, and 11 again, so 10 times faster. But this one is 33 milliseconds, so it's not as fast. Still very fast and much faster than one after the other, but not that fast. Now that's great and all, but there's actually another way to do concurrency requests without using the parallel class, and that is with the Task.WhenAll method. And that's a thing we've talked about in this channel before, but now I want to put it in perspective, because WhenAll is fundamentally different than what you would have if you did parallel. Parallel says, okay, I have 10 engineers, I'm going to split the work that I have to do in 10 segments, I'm going to give it to them, they're going to go do it, and then they're going to come back to me with the results, and I'm going to aggregate them and return them. However, Task.WhenAll, even if you have like 10 tasks to do, it's not necessarily the case that 10 people will do it. It might be that at least 2 people will do it, but maybe not more than 4. And that really depends on a lot of factors, but it's not really something that will hyperutilize your threads. What it will actually do is it will use asynchrony as a concept and say, okay, currently I'm doing this as this person, and this depends on an IO call, which I don't really want to wait for to come back. So what I'm going to do is I'm going to say, okay, this started, I'm going to go to something else. When this thing is back and started, I'm going to come back at it and just tell you the result. And by doing that, you're not really wasting clock cycles. You can do more things at the same time, not in parallel though, just concurrently. And this might or may not be more efficient. I know for a fact it will scale better and will make more good utilization of your system resources without stressing the CPU that much, because it's just fundamentally different concept. But enough with words, let's take a look at how to actually perform. So in order to implement that, it will look something like this. So the WhenAll version is simple as that. You have the tasks that at this point they haven't actually started. None of them has, because they haven't been enumerated yet. They're still in a select enumerable, and then I'm just saying WhenAll and getting the results back, and then I'm returning them as a list. So what I'm gonna do is I'm gonna just run this again, and I'm gonna pull up the metrics again, because I think they are actually interesting when we put them in perspective. This might take a hot minute to run though, so I'll see you at the end. So results are back, and as you can see, and keep an eye on the CPU usage as well, you can see the same trend as before, where we had the degree of parallelism and we went down again when we went to 4. But now you can see the WhenAll version is 23 milliseconds for the same thing. And that's with asynchrony, so it didn't really make the extreme use of threads as saying -1, where we say just use all the resources you can and then the CPU is spiking 100%. But it's still very, very fast, and that's because it used asynchrony and it used that concept of, okay, I'm gonna do something else. When that's ready, I'm gonna come back to that. And that's way more efficient and will actually scale significantly better, and it will perform way more consistently, of course, within the limits of the CPU. And in fact, I actually spun up an Azure VM which only has, I think, 2 vCores. Yes, 2 vCores. And I'm going to put the results right here on the screen right now for you to see. And you can see that the same operation, with the only difference that this actually did 100 iterations, not 1,000. That's the results you're getting. So you can see how much discrepancy there is in when you have a lower quality silicon, how this will perform, as opposed to the WhenAll version, which is actually performing better in that case. Now, remember when I said that you can't really have an async version of Parallel.ForEach? I kind of lied. I mean, it doesn't exist, but you can certainly have it. And I'm actually going to link in the description a blog where there's a great discussion about this very topic. But we are going to actually implement this and compare it in these benchmarks to see where we can get to when we can actually combine partitioning the data with WhenAll, which is effectively what this will do. So this is the method that can allow us to do that very thing. And let me just talk you through that. We have an enumerable of t, which is the source, and then we can select a degree of parallelization. And then we have the body of the function, which is what actually is going to happen. It's what we're going to do within the invocation. And then let's just ignore this nested method for now and go straight down here to the partitioning. We still have Task.WhenAll, but we're using the partitioner class, which is, by the way, a .NET class. This is not a NuGet package. And then you're creating a partition based on the source. You're specifying how many partitions you want to have, and then we use it as parallel to mix parallelization in that. And then we're using select, and we're using this nested method here to await the partition in an iteration fashion. And this gives us basically the best of both worlds, where you can just specify a degree of parallelization here to split the workload in batches and have it as parallel, and then select it and deal with it in an async fashion. And to put it in perspective, this is what the method that will use this method to operate looks like. So as you can see, it's very similar to what we had before. And actually this, you can make an extension method to the parallel class if you want to use that in that way. But basically we're awaiting this operation, which accepts all the tasks, and we specify the batches. In this scenario, it's a parameter. I'm going to show you why I made the parameter to see how it might perform in different threading configurations. And then you can have async await here, because as you can see, this is a function that returns a task, meaning it is an awaitable thing that will properly go through the state machine. And then we're just adding it into the list here. So what I'm gonna do is I'm gonna create 3 methods that have 3 different configurations for the batching here. So first we're gonna do with 1, just to see how this would work with 1, and then with 10, and then with 100. Again, remember we have 1,000 things we want to do per iteration. Now, just a general note on this: you can actually generate this degree of parallelization if you want, based on how many things you have to process. So the batch size, or the total size, can actually give you a batch size, but you have to play with the numbers yourself to figure out what's good for your own CPU. So I won't just give you a number here. That's completely up to you. What I'm going to do is I'm going to just start this benchmark and see what we get with all the things, all 7 benchmarks here on our screen right now. So results are back, and as you can see, the last operation with 100 degree of parallelization actually went haywire, 100% on all logical processors, but it was by far the fastest. Remember, this is doing 1,000 requests, 1,000 API requests per iteration. This is insane. So as you can see, and let's reiterate, for each version, 115 around milliseconds for 1,000 requests. Unlimited parallel version, 11 milliseconds, pretty good. Limited with 4 degree of parallelization, 33. And then WhenAll has 22. And then we go to the parallel async version, which mixes both of them. And one thread, very same performance with the for each version, effectively happens in serial fashion. the 10 batches actually, or degree parallelization actually is 18 milliseconds, so pretty fast. But then when we set it to 100, it made use of as much CPU as possible and it went to 6 milliseconds. And actually, the spike that you saw on the CPU wasn't even because of this benchmark running. It was due to the web API I'm running over here. So that was the process that was consuming the most CPU usage. So if I could move this out of process in a beefy CPU that could actually do much more, then it would perform even better. But you can see that it's by far the fastest. And again, I'm going to show you again how this works. It is mixing WhenAll, partitioning, and parallelization to give you the best of both worlds. But of course, to make full use of it, you would need a very good CPU. So that's where the CPU comes into the picture. With just Task.WhenAll, without any parallelization or true multi-threading, you wouldn't have to worry about that because, like I said, it's asynchronous. It's not necessarily parallel, and threading isn't something you should worry about when you're using async. But in this scenario, you're kind of making use of both. That's all I have for you for today. Thank you very much for watching. Special thanks to my Patreons for making these videos possible. If you want to support me as well, you're going to find the link in the description down below. Leave a like if you like this video, subscribe for more content like this and ring the bell as well, and I'll see you in the next video. Keep coding.